All right. Can you guys hear me okay? Good? All right, well, I guess we'll get started here. Welcome. Glad to see you all today. It's great being back in person after a couple years. I've given a lot of talks in the last few years over Zoom, and well, nice. It's nice to have people that will respond back to me here, so glad to be with y'all. So today I'm going to talk a little bit about batches, streams, and everything in between. We're going to talk a little bit about Lakehouse architectures, Delta Lake, and specifically how that works with the software system that I represent, Apache Pulsar. So before we get into that, a little bit about me. So my name's Addison Hyam. I'm the chief architect / head of product at StreamNative. If you're not familiar with StreamNative, we're the company founded by the original developers of Apache Pulsar. So I've been with StreamNative for about 2 years, but I've been part of the Pulsar community for, 4.5 years. I'm a proud father. Also over the pandemic, became a reluctant dog owner. Had to include him here though. He's a great dog, just doesn't love me as much as my wife. This is us at the Grand Canyon. And I really enjoyed this as a trip we did recently. It was obviously incredibly picturesque, but also really educational, right? I've got young kids. They were really interested in talking about the geological layer cake, right? We build up these layers over time. They form the foundation that we stand on. And the Grand Canyon is just majestic because of that fact. But we're going to talk a little bit about the layer cake of data infrastructure. We'll start with a little bit of a story, a little bit of a narrative here. We'll all pretend we've been at a company. Maybe this company got started about 10 years ago. We got started with some of the early data infrastructure technologies. We have some HDFS, processing text or CSV files, Hadoop, Yarn, data warehouse, traditionally in maybe a traditional relational database system. A few years on, needs change. Technologies change. We layer on this object storage. Maybe we move to Parquet or Orc, some other binary format, Spark batch system, now a columnar database, something like Redshift, maybe it's a little bit more performant. Things change again. We layer on streams, maybe some Spark streaming, real-time relational databases, or real-time OLAP, such as Druid, something along those lines. All the while, we're building applications on top of this foundational infrastructure. Maybe it's for security use cases, compliance, maybe we have legacy workloads. And, in reality, maybe it looks a bit more like this, right? We're building up these sort of infrastructure on top of it. At the same time, we're small teams. We're trying to grow and understand a lot of technologies. They may get a bit out of date. Maybe they're not getting patched. Maybe they're not quite as integrated as they need to be. And we get some of these cracks in the foundation as we apply the weight of these systems on top of these foundational systems. And we're engineers. We like to build things. We like to fix things. And so I'm sure we've all had that feeling, and maybe some of you identify with this, of being like, we got to rebuild it all. Let's fix all these problems. But maybe when we start to engage with that, not going to work so well, right? Huge amounts of investment to go through and really fix and solve all these problems, replace it out with sort of a new foundation. And so it's kind of from this context that I really like to talk about Lakehouse and Lakehouse architectures. I've been in this space for quite a little while. And as that started becoming something in the last few years, it was something that's like, okay, this makes perfect sense to me as an architect. We're using existing formats like Parquet. Makes it really easy to get started with adoption, right? We're not having to go build some new interchange format. We're building on something that already had some establishment. But we're also using that to add some additional capabilities in really kind of a clever way, right? We're being able to get transactions, versioning, all of these different things to fix real pain points to maybe make certain use cases like incremental batch and these higher latency stream processing jobs much more easy. And also that ability to sort of view data both as a table or change stream is incredibly useful. And so we kind of see technologies like Lakehouse architectures as being somewhat of these stabilizing technologies, right? They sort of have these pillars that go driven down to the foundation that give us something a bit more stable to build on. But there's a lot more work to do there, right? The Lakehouse solves for a very important domain, but it's not a panacea. Right, we have it's great for maybe those minute use cases of latency. If you're just here in the previous talk, talked about kind of some of those use cases. But as you really try and get down into maybe sub-seconds, millisecond level latency, there's still kind of a big chasm between how well that works for those sorts of solutions. And there's also just some of the same traditional challenges. You know, we have data in the application tier being produced. We need to get that still into the data tier. If you're not using a streaming solution, that's still a challenge. And it's often also a one-way operation, right? We're getting data into the Lakehouse, into these Delta table formats, but sometimes getting them back out into the application tier, say from, say, an ML workload, for example, can be, there's still lots of ways to do that, can be a challenge. Data governance, you know, you have different systems for your kind of real-time streaming system versus maybe Lakehouse, and just generally, you know, having a true event-first kind of comprehensive data platform is just a big, complex place. You know, really, it actually looks a bit more like this, right? We have underpinning this all of the kind of layer cake of the infrastructure tier. Not to mention the application tier, which has its own years of building up layers of complexity. And in many organizations, all of this exists all at once. Okay, so with that kind of context here, I want to start talking a little bit about Pulsar. And because we're in person and I get to do this now, who by raise of hands has heard about Apache Pulsar? Okay, a few of you. Any hands on who has, you know, deployed an application with it in production or otherwise? Okay, well, then we got the right audience here today. So I'm going to get started with kind of a brief introduction of what Pulsar is, why it matters, and then we'll get into really talking about some of the magic kind of that comes together with Delta Lake. And so at a high level, you know, I like to talk about Pulsar. It's the unified messaging and streaming platform for real-time teams. And unified messaging and streaming, what do I mean by that? Oftentimes the system that, you know, Pulsar most gets compared with is obviously Kafka, right? And by no means is my message to you today is like, oh, go, you know, replace all your Kafka with Pulsar. Really, they solve a different problem, and they really come from the problem at a different perspective. And one way to think about that is Pulsar is really designed from the get-go of being like a platform technology, being a technology that you're going to use across the foundation of your organization. So that's why, you know, Pulsar has its own API that we say that supports both messaging and streaming codes, which I'll talk about, but also natively supports other APIs. So if you have RabbitMQ, MQTT, Kafka API, that's natively supported, as well as functions, connectors, you know, lightweight compute, as well as the ability to interconnect with other tools that's integrated within Pulsar, included in the core, as well as a lot of what I kind of call platform features. One of these most important ones is multi-tenancy. So you can say, okay, instead of having to have like lots of different clusters, Pulsar is really designed to have, you know, one cluster that can support many teams, many workloads at once, as well as things like gReplication, tiered storage. Those are all built into the open source, because once again, it really was designed to be a multi-tenant messaging system for organizations. One way to look at this is really, I like to say, it's kind of the right API for all types of asynchronous data. It's not messaging, it's not streaming, it's really both. That means it's optimized for really high scale, like you might have in streaming use cases, but also has the guarantees and durability you would expect for sort of mission-critical application messaging. Has a familiar PubSub API. This is actually personally the thing that I first kind of fell in love with in Pulsar, is that trying to kind of teach teams streaming workloads and messaging workloads and how they were different, and like why a work queue and why a stream are different. Pulsar just had a simple API that I was able to work with my developers that say, oh, I get this, I understand, I can use it. And once again, this support for both messaging and streaming workloads. And kind of returning back to that, you know, concept of like the right tools for the platform, right? For something that you can use across your organization. That's the built-in multi-tenancy, which is not just, hey, we have multi-tenancy and we can simplify having to deploy lots of clusters. It also enables kind of new use cases in your organization where rather than having to build a system on top to sort of figure out, okay, which data is where, it's a problem within Pulsar, within the platform, to really kind of break down those data silos that often grow in organizations. Support for Kubernetes and gReplication. You know, I'm sure many of you here, there was questions in the last talk relative to, hey, I need to build across multiple cloud providers, multiple regions, and having a tool that natively supports that, as well as mention that built-in tiered storage, which we'll kind of end the talk with today of talking about that tiered storage feature. As a brief history of Pulsar, so it was actually initially developed in Yahoo is the cloud messaging service. It was actually initially designed to replace JMS workloads. So you know, if you know a little bit of the history of Kafka and how that came to be, it's very different from Pulsar. It was really squarely designed to solve in this sort of core application messaging space. In 2016, that was open source. In 2018, became an Apache top-level project. And then the company I work for, StreamNative, we were founded in 2019 by, once again, some of the original developers on the project. 2020 was a lot of focus on ecosystem. So Spark, Flink, bringing those connectors since that is such a critical aspect. One note in 2021, we were really, so Pulsar, is a bigger system. And so we expect to have more contributors than maybe some other projects. But we have had, since 2021, like more monthly active contributors than Kafka on the project, where we've really seen, organizations trusting and betting on it for their technology. And so during this period, we saw adoption from organizations like Tencent, Splunk, Iterable, and a growing number of customers that are, community members or customers that are using Pulsar, like Fortune 100, Fortune 500 companies, banking, finance, all of those typical things you would expect. And really in 2022, we've only seen that trend kind of continue. So once again, you can kind of see Pulsar as being a combination of taking the feature set about a use cases like message queuing, traditional application messaging, systems like ActiveMQ, RabbitMQ, et cetera, as well as data streaming use cases, Kafka, Kinesis, et cetera. Both of those run really well on Pulsar. And how do we do this? So now we're gonna we're gonna start getting technical here. Pulsar is really the right architecture for unified data. What I like to say is that a lot of people will say, well, why make these choices? And a lot of these choices are actually, it's the right amount of complexity to solve for a complex problem. So we separate the compute and the storage in Pulsar, and you treat them as separate tiers. We'll go into why we do that, but one of the things is that it's really about easier scalability and also allow us to evolve that platform rapidly, to add new features and kind of innovate because we've decoupled two very hard problems into two separate problems. And both of those, there's a pluggable metadata storage. That's something like Zookeeper, etcd, et cetera. We have that as a pluggable dependency. One of the aspects of this is it makes it really easy to run on Kubernetes and cloud. Once again, getting a little bit into this data modeling. One of the things that's great about this for maybe data architects, application developers, et cetera, is rather than having kind of map your problem onto the constraints of another system, you get the flexibility to use maybe more of a streaming style or like a messaging style topic where you're not, instead of using partitions, you may have large numbers of topics that, for example, many of the community users are using like a topic per customer, for example. Maybe their tenancy are mapped in their topics, which gives you a lot of design space to work with. And all this means you can support things like work queues, fan-out patterns, or key-based, topic-based ordering like you'd get in a streaming system, as well as a support for different protocols within native Pulsar. Okay. Oh, well, not quite sure why this went weird on this screen, but the way we do this, the way we provide all this flexibility is you have, much like many messaging systems, a producer producing data, a topic that stores messages, and then we have the magic of Pulsar is these multiple different subscriptions. So you have a key shared, a failover exclusive subscription, or a shared subscription. And each of these have different semantics. So in a key shared subscription, that gives you the ability to have many consumers, but get a key-based ordering. So pretty unique feature of Pulsar. If you come from the Kafka space, the failover subscription is semantically equivalent to a Kafka consumer group. It means you're getting topic-based ordering or partition-based ordering, but you only have one active consumer. Or you can get kind of a pure messaging work queue, where you don't have the order guarantees, but you get as many consumers as you want, and it works very much like a normal work queue. So kind of put this a bit more visually, these different ways you can build a system. So I can have many topics that I'm using individually. Once again, maybe I'm partitioning my data by customer or by application, lots of different ways you can do that. Or I can use partition topics and use key-based partitioning to scale up my system that way. Both are an option in Pulsar. Within a topic, we have a mechanism called segments. So in a given topic, only one segment is open at a time. And that open segment, that's the segment that's receiving active writes. Once that segment, over some period of time, either based on size of how much data you've gotten or on time, that segment will close. It becomes read-only. But you can still obviously read that like you would in a streaming system. And so what this means in Pulsar's architecture is we have brokers that are serving topics, and bookkeepers, this is the storage tier of Pulsar, that are serving segments. This architecture allows us to do rebalance-free scaling. So if maybe some of you are familiar with Kafka or other systems where the storage and compute are coupled, adding new capacity can be a challenge. With Pulsar, because the broker tier is stateless, and because we're always rolling over to new segments periodically, when we add new capacity, the system will automatically notice that, rebalance the cluster, and give you additional capacity at both the compute tier, the brokers, as well as the storage tier at Bookkeeper. This also means that things like high availability are really simple in Pulsar. A broker crashes, the system responds to that and moves the ownership of that topic, as well as any producer or consumers that were working on that topic actively, to a new broker. Likewise, the bookkeeper tier, if the bookkeeper crashes and anyway has a fault, we close those segments. We say, okay, I'm closing these segments. I've been writing to multiple, but I'm going to now choose a new group of bookkeepers that I'm writing my next segment to. And so that's what allows us to keep both write and read availability by choosing a new group of bookkeepers and then obviously having replicas of us writing to multiple bookkeepers in the storage tier at once. And finally, the thing we'll, once again, kind of talk a little bit more towards the end of the day is the storage offloading. Because we have this segment-based architecture in Pulsar, it's really easy for us to move those closed segments that are read-only, they're not being modified, move them onto commodity object storage, AWS, Azure, et cetera, and then we actually read that data directly in the compute tier now and allow us to not have to worry about managing those disks and whatnot for long-term retention, making things like infinite data retention really quite a bit simpler. Okay. So now let's talk about Pulsar and Delta Lake together. Obviously, we're in kind of different, Pulsar and Delta Lake, they have different domains. They're solving different problems, but actually have fairly similar goals in a lot of ways. They're really both kind of designed to fix gaps in the ecosystem by providing kind of the right APIs for the domain. In Delta Lake, Lakehouse architectures, that means giving these guarantees of transactions, change feeds over traditional data lakes. With Pulsar, that means giving us the APIs for both messaging and streaming use cases. Both are designed to play well with other systems, right? There's a strong aspect of, obviously, an open interchange format like Delta Lake, as well as with Pulsar of really integrating well with lots of other systems and not trying to replace everything else, right? Like Pulsar is not a system to say, hey, means go immediately replace all your RabbitMQ applications and rewrite those. That's why we support these other protocols natively within the system. And really, I think what's really kind of fun for me as an architect is that they're both really born out of some of the innovations we've had from cloud tooling, right? Whether that be object storage, whether that be things like Kubernetes. As we start getting more and more of these systems, we're seeing these innovative tools like Delta Lake, like Pulsar, that help solve problems. And both are being used by organizations to solve those problems. Okay, so we're going to kind of return to why these two systems together. What's kind of the magic here? And once again, where Pulsar is really strong on sort of unifying your application and data tiers. It's a system that works very well in a microservices environment for having a strong messaging backbone. But because it also supports those streaming workloads, it works really well in the data tier and makes it so you have kind of one tool as opposed to many organizations that maybe run a messaging system, RabbitMQ, et cetera, in the messaging tier, and maybe a streaming system like Kafka or Kinesis in the data tier. One system to kind of simplify the process of getting data between those two different tiers. And likewise, Delta Lake kind of extends that further, right? Because now we can take a Pulsar topic, and we can now give us a mechanism for reading that topic in a very simple way as a Delta Lake table, giving us the ability to sort of view our topics as tables. And this really together means that we're covering a wide domain of the problem space, from sort of very front when data is produced in the application tier down to the long tail and sort of longer lived use cases that we might have in batch workloads, traditional analytics, et cetera. So there's really kind of a pipeline throughout that whole sort of life cycle. And so to kind of give some illustration of that, we'll walk through a few different examples. So first, let's kind of set the stage here. So we've got things like Pulsar, Delta Lake, Spark, use cases that we may have that we're connecting via our I/O connectors. These are parts of Pulsar that allow it to get data from other systems easily, as well as Pulsar APIs itself, and maybe use cases that are more at the like sort of the AI and analytics, AI, ML workloads. So once again, this allows Pulsar to have its own features, things like Pulsar's protocol, what we call Kafka on Pulsar, that's the support for Kafka API, RabbitMQ on Pulsar, as well as all these other connectors. Obviously, is there an integration between Pulsar and Delta Lake? We'll talk a little bit about that. That allows us to take a Pulsar topic and view it as a Delta Lake table, or to take a Delta Lake table and read it as a topic. And then obviously, kind of another important piece of this is the Spark compute side of things that allows us to not just read data out of Pulsar, but also run computation, write that data back into Pulsar, et cetera. So an example use case. So we have an application, living in the application tier. That team is using Pulsar for their own application. Now, instead of having to go have that team do like another integration to get the data into a streaming system and then into Delta Lake, because you've already have that integration, the team is using that in the application tier, adding on Delta Lake, getting that out to a table for, say, a use case in ML is very simple with these integrations. But kind of what I think more interesting is often more the challenge is, okay, now we have some results from this ML workload. Maybe those are like a longer term sort of batch style ML, and we want to make that available to applications. That gives us the ability to now take that data out of Delta Lake into a topic in Pulsar and back into the application tier. Obviously, there's use cases where maybe it's not the raw data, but we could use something like Spark to transform that data into Delta Lake tables that may not be the best practice for us to take our raw change data capture data and put that straight into Delta Lake. So we can use Spark as sort of an intermediary there to help us enrich, clean up that data, et cetera. Or finally, a use case where not every system is yet integrated with Delta Lake to the level we would like. Perhaps something like a RabbitMQ that doesn't have a native integration. We can read that data into Pulsar, then into Delta Lake, making it available for other use cases. So we'll get in a little more detail in these pieces. So once again, the first piece of that is the Spark Pulsar connector. So if you're not familiar, the Pulsar Spark connector, this is a really full-featured connector between Spark and Pulsar. Supports native SQL, Spark SQL, et cetera, as well as full schema support. So should be mentioned, Pulsar has a built-in schema registry. You don't have to have like two different systems. It'll natively support that and take a Pulsar topic and allow you to run a SQL query over, for example. That supports kind of latest Spark and Pulsar versions and is being used pretty heavily in production across a lot of organizations that are in the Spark and Pulsar ecosystems. But we're more want to talk about today, and we're really excited actually for the initial release of, is the Pulsar Lakehouse connector. So this actually supports not just Delta Lake, but also other formats like Hudi, Iceberg, for writing into those formats. So taking a Pulsar topic and getting it into one of these Lakehouse style formats, but also supports with Delta Lake reading that into a Pulsar topic. We'll kind of do a demo of that in a moment. And one of the nice things about the Pulsar connector framework is this runs fully managed in Pulsar. It's not like a separate component you deploy. It's part of Pulsar. We'll see that, and that can either mean that it's running in a local process or actually run out on your Kubernetes cluster, for example. And this means it also doesn't depend on a Spark cluster. You don't need to go deploy a Spark cluster just to get this data in and out. Once again, it's newly released. If you're interested in this, if you're in this, please reach out to me afterwards. Happy to chat a little bit more about it. But I'm going to do just kind of a very quick 2-minute demo here. And this is always the thing with demos is like, do I risk doing it live? How brave am I feeling? Yeah, we'll go for it. So what I'm going to do is I'm going to start Pulsar standalone. Oops. I forgot that I was just doing this locally. So this is a brand new Pulsar cluster. If you download Pulsar, obviously you're going to see a lot of data here. But this is just me running a local Pulsar. It's kind of a single command to get Pulsar up and running. Oops. Next, what I'm going to do is I'm going to start. I've got just a very small Spark SQL, or excuse me, PySpark job that is using some nice utilities that exist in the ecosystem for generating a streaming Delta Lake table. So I'm writing about 25 rows per second. I've got some pretty simple schema, and this is just some utility that exists to generate data, and I'm writing that as a Delta Lake table. So I'm going to use my cheat scripts here, though, because I will screw up writing the command. So that's just going to kick that off and write that. And so we can see I now have this, I have a data directory where I've got, sort of what you would expect. I'll make that a little bit. I've got a Delta log, I've got Parquet files that are being written out. And now what I'm going to do is I am going to start this source. So this is going to be a Pulsar source that's reading data from a Delta Lake table and into a Pulsar topic. And so this is just a very simple command. This is how we do this in Pulsar. We point it as source configuration. And that source configuration basically says, OK, here's the code for my connector. And I'm going to write that to this test Delta Pulsar. And here's some options of, hey, I want to use the Delta format. I'm going to checkpoint every 30 seconds. Here's where I want to write that. I'm just using local files. I don't trust conference Wi-Fi enough otherwise. And other parameters relative to that. So I'm going to start this source. I'm going to let that kick off. And that's just actually going to get, once again, this is being fully managed in Pulsar. So if I actually run my Java process, I can see that I've got a, actually I'm not sure which one of this process is, but I've got an additional process that was forked off. Once again, it's fully managed by the Pulsar connector framework. And now I'm going to run this other command to get my topic stats here. So this is just a command in Pulsar that allows me to look at what's happening on this topic. And we're just going to take a look at that. So I can see that I have on this topic, there is a producer, a publisher. These message rates are a little bit latent in calculation, so you only see 3 messages a second, but I can see that I'm actively writing data, and I've written 275 messages. And so what we're going to do is now I'm going to start this is just a very simple utility to kind of pull in data, read that, and subscribe to that topic. So I'm just going to start this consumer so we can see that, in fact, I'm getting this data. Oh, actually, I wanted to do one other thing. What I want to point out here is that I also can have a little command here that is just going to show me the schema. Because one of these important aspects is schema. And so we can see that this topic, once again, it's a brand new Pulsar, didn't know about this topic before. We created the topic, and we also passed the schema information from the Delta Lake table. I guess I'll show that a bit more. This is just that format of all the different fields we had there, strings, types, whatnot, and this actually gets translated into an Avro record. And now we're going to start this consumer, and we'll see that this will take a minute because this is just going to consume the data. It's not going to show us every record, but will instead show that we are consuming and give us stats on how many messages we're seeing. So we got a lot of messages because we built up a bit of a backlog. And now the next time this reports data, because we're sending 25 messages a second from the data generator, we're seeing roughly 25 messages a second here. And then finally, we're going to write this data back out. So we're going to look at the sync configuration. Looks very similar, gets run a similar way, but now we're just going to write this data back to my local file system. I'll use it in a very realistic use case, but we're going to see kind of this data go back and forth between the two different systems. Let this get started. Once again, this is getting managed entirely by Pulsar. If I was doing this not on a local cluster, but on a production-grade Pulsar cluster, that would actually be running that as like a Kubernetes pod. And I can now see that on this out data folder, I have what I expect with some Parquet files, although I think this actually hasn't dumped yet because of the checkpoint interval and whatnot. But once again, that's all running, and we'll continue to now move the data back from Pulsar into that. So once again, here's the visual here. We went from Spark into Delta Lake, then took a Delta Lake into Delta Lake source into Pulsar, and then back out to Delta Lake. Talk a little bit about how this works. So Pulsar, the Lakehouse connectors and the Delta Lakehouse connector is built upon the Delta Lake standalone. And so we're actually using the Delta Lake log via the APIs provided in the Delta standalone to get this change of metadata where we're seeing new files, whether files are removed, getting those Parquet files, turning those into records, and writing them in a topic. As well as on the schema side, if there's metadata changes, whatnot, we're updating that schema appropriately. And once again, in this case, I was running that locally, but in a real Pulsar cluster, that actually be running in Kubernetes. Okay, so as I kind of mentioned, one of the things that all exists today, and if you have questions, use cases for that, happy to chat more about it. But I wanted to mention real things. This is just the start for where we see Pulsar working with Lakehouse style formats. One of the challenges that we sort of see in this space is that there is still kind of exists this gulf between my streams and my batch data. And Lakehouse is really a great bridge towards that. And so we're actually actively working on the ability to take that tiered storage solution, that storage offloading, and natively support Lakehouse. So instead of having to run a connector, instead that when we move those segments that we mentioned earlier, Once those closed, we transform those into Parquet files right away and put those into Delta Lake, into a Delta Lake format. What I like to kind of call the write once, read everywhere. So you write it into Pulsar, and now you have the ability to continue to read that data via streams in Pulsar, but also to view it as like a lakehouse table. Really giving you kind of the ability to think about like an end-to-end data lifecycle management. So we're really excited about this, and if, get connected with the community and we can chat more. So yeah, with that in mind, hopefully this is a good introduction for you guys to get a bit to know about Pulsar, why we're so excited about the Lakehouse, and encourage you to get involved with the community. The Pulsar website has a lot more details, but as well as the Slack community. If you're interested, ping me there. Happy to see it. As well as if you want to get started with Stream Native, we have a full-fledged cloud offering that kind of makes the concerns of running Pulsar, and you can start with that console, Stream Native Cloud. Also, if you want to learn a lot more, we have our Stream Native Academy. It's a great place for you to be able to kind of learn about Pulsar, get started, get the 101 with both on-demand courses as well as instructor-led. And those on-demand courses are totally free, whatnot, just for people to make it easy to learn Pulsar. And if you're really interested, join us at the Pulsar Summit. So that'll be August 18th at the Hotel Nico in San Francisco, here in San Francisco. And you can get your early bird tickets now and whatnot. And finally, hackathon coming up. So I think we're about that out for time here. I don't think there may be a moment or two for questions. So yeah, thank you so much for your time here, and we'll take questions.